This video is an introduction to the heat pump. Now, heat pumps are very popular in the southern part of the country, specifically where the winters are not hitting 0-degree conditions. However, that's starting to change as well, and we're seeing heat pumps move further north, but we'll talk more about that. So, a heat pump leads all other forms of heat in terms of efficiency and low operating cost. The demand for heat pumps has increased because of the dramatic increase in the cost for all other forms of energy. They must be installed correctly to take advantage of the energy-saving technology. You must follow manufacturer's guidelines when installing heat pumps. Heat pumps derive their name from the manner in which heat is delivered into the home or office. They're not producing heat, as in the case of a fuel-fired or electrical furnace, but they're actually pumping heat from one area to another. Their efficiency is rated not by how efficiently they consume energy, but by rather how efficiently they move it. Little bit of background. The popularity of the heat pump rose with increasing costs of electrical energy used for heating in residential and small commercial buildings. Heat pumps generally cost a third of what it costs to operate electrical heat strips. Now, the heat pump was developed by a guy named Lord Kelvin back in 1852, so it's not brand new technology. It just has evolved over time. The first practically applied heat pump was installed in Scotland in 1927. Between 1927 and 1950, heat pumps were installed in hundreds of homes and small commercial buildings throughout Europe and the southern part of the U.S. Many were simply air conditioners converted to heat pumps by the addition of a reversing valve and applicable controls. These early heat pumps often failed because they did not have defrost controls, crankcase heaters, or suction accumulators. They developed a bad reputation because of this. Although improvements in design were made, making them more reliable, the early failure rates still caused problems in the market for years. Today, the demand for heat pumps has grown. The reason for this newfound interest in them is because of economics and environmental issues. It has also grown because of the growing interest in energy conservation, the rising cost of heating, and the pollution produced by power plants. Like refrigeration and air conditioning systems, heat pumps transfer heat from one place to another by changing the state of a refrigerant. Basically, all refrigeration systems are heat pump. They transfer heat from a heat source at a low temperature to a heat sink at a higher temperature. What makes the heat pump so unique is the ability to reverse direction of this refrigerant flow. In the summer, it removes heat from the inside air and moves the heat to the outside air. In the winter, it will remove heat from the outside air and move it to the inside air. Heat pumps are also referred to as reverse cycle refrigeration systems. So let's talk about some basic principles that will help us better understand this concept. Heat exists down to an absolute zero temperature. Absolute zero is negative 460 degrees. So heat exists in the air down to absolute zero. Gases become warmer when they're compressed, okay, and we see that in the compressor side of any refrigeration system. When you compress it and raise the pressure, the gas becomes warmer. Most matter can be in a solid, ice, like ice, liquid as in water, or gas as in steam state. The temperature at which material changes state from a liquid to a gas or from a gas to a liquid depends on the pressure at which it is contained. So the first concept is heat in cold air. One of the biggest obstacles to overcome for many people in the understanding of heat pump operation is accepting the fact that heat exists at very cold temperature. You can be outside and feel cold, but there's still heat in that air. Heat is a form of energy that gives molecules their motion, and all molecules are in motion. Therefore, all molecules contain heat. The only exception to that statement is when the temperature reaches absolute zero. At absolute zero, molecules do not move. When they stop moving, heat no longer exists. Concept number 2 of heat pump operation As with any refrigerant system, heat flows from high to low. Heat will always flow from high temperature to a lower temperature. No mechanics are needed for this. This is basic physics. The job of the heat pump is to make heat flow from a cooler area to a warmer area. To do this, the heat pump has a low side, which is colder than the cool area, and it also has a high side, which is warmer than the warm area. Moving heat from the low side to the high side is where the name pump comes from. Concept number 3, compression raises temperature, expansion lowers temperature. The high side is created by compressing or squeezing the gas. When gas is compressed, the heat in the gas is concentrated and the temperature rises. This portion is accomplished by the compressor. When we expand the gas or liquid, its pressure and temperature will drop. This is accomplished by the expansion valve. The compressor compresses the gas, raising the pressure and the temperature. The expansion valve expands the gas, lowering the pressure and the temperature. Concept number 4, the change of state. In other words, liquid to gas, gas to liquid. It's possible to build a heat pump just by compressing and expanding gas. The change of state of a refrigerant will dramatically increase the efficiency of the heat pump. Liquid absorbs about 100 times more heat when they change state than when they change temperature. Remember, change of temperature is sensible heat. Change of state is latent heat. So let's just give it an example of water. When we change sensible heat, okay, we're just adding 1 BTU of sensible heat is 1 degree Fahrenheit for 1 pound of water. Latent heat is significantly more, by about 100 times. With this in mind, the refrigerant evaporates from a liquid to a gas in the evaporator, or when we're talking heat pumps, the indoor coil or outdoor coil, okay? Because the evaporator moves. It condenses gas from a liquid. It condenses from a gas to a liquid in the condenser. And again, the condenser in the heat pump is not always in the outdoor unit. That's the other thing you got to really remember. Concept number 5 is saturation temperature and pressure. The temperature at which evaporation and condensation will take place is controlled by pressure. The increase in pressure on the high side raises the condensing temperature, allowing the condenser to reject large amounts of heat when condensing the refrigerant. The decrease pressure on the low side lowers the evaporation temperature, allowing the evaporator to absorb large amounts of heat while the refrigerant evaporates. So the whole purpose is that the high side, which is the condenser, has a temperature that is higher than the surrounding ambient air. On the evaporator, the temperature is lower than the surrounding air, and we accomplish this by changing pressures. The biggest obstacle to accepting heat pumps by customers is the relatively cool supply air temperatures that heat pumps produce. Many customers have been used to traditional furnaces, and they often complain about cool supply air from heat pumps. A typical heat pump supplies air temperatures from about 95 to 110 degrees. Electric heat has discharge temperature from 110 to 125 degrees, and fossil fuel burning equipment like oil or gas supply temperature ranges from about 120 to 140 degrees. 95-degree air blowing across the body in the middle of the winter will feel drafty. The solution to this problem is proper supply register placement. Supply registers for heat pump systems should not blow directly on the occupants. Heat pumps are designed to heat the space, not you. There's 2 other terms we have to talk about. I already mentioned them once: heat source and heat sink. The heat source is where the heat comes from when the heat pump is operating in the heating cycle. Typically, the source can be either water or air. Air source heat pumps pull heat out of the surrounding air. Water source heat pumps pull heat out of the water circulated through them. The heat sink is where the heat pump puts the heat. The heat sink is often assumed to be air since most heat pumps are designed to condition the air in a space. Water source heat pumps only mention the source because the sink is assumed to be air. That would be geothermal type heat pumps. However, water-to-water heat pumps use water as both the source and the sink. But notice that water-to-water is actually named. So we have different types of heat pumps, and this table lists them by the source and the sink. So for an air source heat pump, the source is outdoor air, sink is indoor air. We use heating homes and offices with forced air. Water source or geothermal, the source is groundwater, the sink is indoor air, and again, heating homes or offices with forced air. Air to water, the source is indoor air, the sink is domestic hot water. We use this for domestic hot water heaters. Water to water would be the source being a groundwater, the sink is a water loop, and we can use this for heating homes with hydronic radiant heat. Usually water to water is only used in the winter or in heating mode. Heat pumps come in different configurations to match the many different applications. They include packaged units, split systems, ductless mini split systems. Package units comes with all the system components assembled together in one package. They're available to fit different physical space requirements, including some are made for outdoor unit installation, some are designed to be over drop ceilings, and some are through the wall or mounted on the wall. Traditional air source package heat pumps are designed for the entire unit to sit outside. You see these a lot on commercial buildings, package units, or you sometimes see them residential package units. You see them sitting next to pre-manufactured housing. Horizontal water source package units are designed to be installed over a drop ceiling. They're compact and can fit in small places above the ceilings. You see these in office buildings and apartments a lot of times, where there's a water loop that circulates through the entire building. Packaged terminal heat pump units fit through sleeve in the wall of the motel rooms. This is what you see in most of the hotels and motels around the country. Wall mount package units are vertical source heat pumps that bolt directly to the wall. These are often used for large open meeting rooms, computer rooms, cell towers, etc. You see the units mounted on the outside. Now, split systems are different than the package units because split systems break the unit into two separate components. They're connected through refrigeration lines. Split systems consist of an indoor unit and an outdoor unit and a line set. The outdoor unit will house the compressor, condenser coil, metering device, and reversing valve in most of the system controls. The indoor unit will house the blower, the evaporator coil, and the metering device. Notice there are two metering devices in split system heat pumps. This is an example of a split system. You have your outdoor unit on the bottom left, indoor unit right side, and because of International Mechanical Code, we are required to install electric heat in any system with a heat pump. Now, we also use the electric heat when we go into defrost mode, which we'll talk about in a future presentation. But you will always find electrical backup heat in any heat pump unit. Ductless mini splits are similar to split systems, except they're designed without ductwork attached to them. The indoor unit is designed to be installed in the space being conditioned. Mini splits are available that connect up to 8 indoor sections to a single outdoor unit because they provide zone comfort control without ductwork. The metering device in a ductless system is only located in an outdoor unit of the mini split heat pump system. Both the liquid line and the suction lines are both insulated because of the single metering device. Regardless of what mode the unit is in, the refrigerant is passing through the metering device. This is an example of the ductless mini split. You have one outdoor unit with multiple indoor units. Each of those indoor units will have a line set that goes to it, unless it's a Daikin system. And we'll talk more about Daikin systems in the future. They're a little bit different. I mentioned air to water heat pumps being domestic water heaters, okay? If you're in an area of the country that actually has warmer temperatures, you might see these in someone's garage or even sometimes outside, even though it's not recommended. Okay, what it's actually doing is it's circulating water, okay, through, basically it's heating the water by de-superheating and condensing the refrigerant of a small refrigeration system. Okay, you see you have a refrigeration system, you have your warm air coming in, passes across the compressor just to help cool the compressor a little bit. Okay, comes through an evaporator coil, okay, which is actually picking up heat, and then comes back to the compressor. Now the discharge gas from the compressor goes to a condenser that is mounted alongside the water heater in this case. There's some variations of this also that the water is circulated through a tube-in-tube heat exchanger as well. Both are available. So just be aware when you look at these. They still sometimes have an electric coil in it in case the temperatures get too cool, but that rarely happens. So that's an introduction to the heat pumps, the various types. The next thing we're going to do is talk about the reversing valve in the next presentation.